All right, so it's time for the Predicting Precipitates lab. Woo! Okay, so realistically, today's lab is about figuring out if things are going to form and how would you do a precipitate lab in practice? How would you actually test this stuff in a lab? And so we're going to need some chemicals. So let me clear my workspace here really quickly. So in no particular order, let's introduce our chemicals. I've got some sodium phosphate. Sodium phosphate is a relatively rare chemical. I've got some potassium nitrate. This is like the most important chemical in making gunpowder. Got some lead nitrate. That's familiar to us. Lead nitrate's really heavy for its size. It's lead. Got some potassium iodide. Pretty useful chemical in the lab. Iron 3 nitrate. Again, kind of a little bit rarer chemical. Worth noting. I've got some sodium hydroxide in the form you can buy it in like a hardware store. Got some aluminum chloride here. I need to change that out for ammonium chloride. I grabbed the wrong one. Aluminum chloride is not going to work for us. But I'll change it out. So this will say ammonium chloride instead of aluminum chloride. Actually, for a second, what would the formula of ammonium chloride be? If it's not this, it would be what? I've also got this Erlenmeyer flask, which notice coated entirely in dark paper towels and covered in stains around the top. So it's really important not to get silver nitrate on your hands. It will stain them. Now this chemical is incredibly important to early photography, right? This is how you get early pictures. Well, different silver compounds like the nitrate. Really, the chloride and the bromide probably matter more to photography. But that's besides the point. This one also is like it. So knowing this was useful in photography, why do you think my silver nitrate is wrapped up like this? Right, so this is a light-sensitive chemical. And it's not like if I let the light in right now, oh no, all of the chemical's gone bad. Like, it takes time, but you have to protect it, especially because silver is a valuable metal. We don't want to mess up the solution. So you'll often find chemists storing it in something like this. Now, the problem is, of course, if I take any of my other things, I think this iron nitrate here is kind of cool looking as I look into it. It's in a solid form, and solid form chemicals aren't going to work for me. And so what I need to do is I need to make this into a solution, right? All of the things I have, including now my properly sourced ammonium chloride, not aluminum chloride, so here we are, ammonium, right, are in that salt form. And I don't want them in the solid form. I want them in a different state of matter, which allows them to break into their ions. So what symbol would tell me that I have a chemical which, put in water, will break apart or disassociate? You know, I was thinking about it. Let's add one more salt to this. Just because all the other ones are white powders, let's have a little color mix in. So this is copper 2 sulfate, CuSO4. You can see it's got a couple different colors going on here. What's going on with that is this has got water in it, and this is starting to dry out. It's not going to change anything for us, but let's throw some copper in there. Okay, so I need to make aqueous solutions of all of these. And the concentration doesn't really matter. Now, you don't actually understand what concentration means to a chemist, but you can think about like the amount of this per milliliter of water is really kind of insignificant to my end result. So let's go ahead and prepare a simple solution of, I don't know, let's start off with the sodium hydroxide here. All right, so there's some sodium hydroxide. You can see it's just a white crystal powder. Relatively dangerous, this stuff. If you get it on your skin, it will turn it to soap. Now, this isn't an acid. It's the opposite of an acid. And I know we haven't actually covered that just yet, but still I want to ask the question here. What's the opposite of an acid called? All right, so I'm going to add my salt to a test tube. And you can see there's not a lot in there, right? I don't need a lot to do this lab. I just need a little bit in there. Now, that's not aqueous. So what do I need to add to the test tube to make this a solution? All right, so I'm going to use this distilled water, and I've got my salt in there. And it's not dissolving right off the bat, of course. So I'm going to need to sit here and mix it. Now, this chemical is relatively dangerous. I don't necessarily want it on my fingers. And you can see this takes some time. Chemists are lazy people, and I don't want to do this for very long. So actually, I have an idea. All right, perfect. So this So this thing is called a vortexer, and it's just a little motor with a dial on the front and this little rubber thing on the top, right? And what's cool about this is if I set it upright, I take my test tube here and I just push down on it. Hey, it shakes things, right? But what's really nice about that is I don't have to sit here and flick it or shake it or whatever, and it's just stirring. Now, it hasn't dissolved all that sodium hydroxide. It's going to take it a moment. But that's a lot better than me having to do this by hand, right? I can just sit here and I can vortex it up. Now, as I do this, this solution is getting hotter. It's releasing heat. It's been a little bit of time, but we had a name for that in chemistry. So what would we call a reaction that generates heat? Right, so this is an exothermic. Exo means giving off heat. And you can see I've dissolved all the sodium hydroxide. Now, while we're here, I said this would turn my fingers to soap, and here it is. I've got some on my fingers, and I'm not going to panic. This is very weak, but I can feel my fingers a little bit slippery, kind of like there's soap on them, and that is the outermost part of my skin turning to soap there. Now, I'm going to quickly go wash my hands just because you never want to mess with those things too much. Bases are dangerous. But we now have our first solution, and I can keep it off to the side here and keep track of number one is sodium hydroxide, and I've got a test tube. Now, I'm not going to walk you through all of these. I'm just going to make a time lapse of me making things up here. So hold tight. So while we're here, this is the copper sulfate solution. I want you to notice its color. This might be the first time you've actually seen a copper solution. So all copper solutions in a chemistry lab, or at least many of them, take on what color? All right, I'm going to restart the time lapse here in just a second, but all copper tends to be blue. Let's go ahead and do the iron nitrate next, though, in this time lapse. I want to point out how much harder this one is to dissolve than others. Just because something is soluble doesn't mean that it's necessarily easily soluble. So you might have noticed I've been sitting here with the vortexer longer on this one to get this phosphate dissolved. That's not terribly surprising to me, but it still needs a little bit more, so here we go. Hey, when I feel this one here, it's the opposite of hot. It's actually really cold. So if a reaction gets cold, then what would it be called? I also want to point out how much easier that was to dissolve than the phosphate. It makes some sense when you're all said and done. One here also should probably point out that you might have noticed my fingers turning a little yellow as we're going along. That's the iodide from the Ki. Whatever. Okay, I think we got one or two left. Just one left. We're going to do the ammonium chloride real fast. All right, and I guess we should also pour in a little bit of silver nitrate really fast. All right, so it's kind of hard to believe, but this liquid here that's really transparent, right? You can see my hands through it. It just looks like clear. It contains precious metals. It contains silver. Right here, this is probably well north of $1 worth of solution. Now, I did something I should never really do, which is I took chemicals that I had poured out and returned them back to my stock container. That's a big no-no. But I did it because it's valuable, and I just cleaned these test tubes. I know that for a fact they're clean, right? I know there's no contamination. Still shouldn't really do that in a lab. So all of that work has netted us all our test chemicals. Now, you're not going to see them in this form again, but I wanted to show you that, right? A few of them here, like the iron nitrate, do have color. Most of them, though, as you'll notice, are clear, water-looking liquids, which is a common issue in a lab. So I've been careful and I've written down what everything is in order so I can keep track of that. I want to point out this was not a short amount of time. In real life, this took almost 25 minutes just to make this rack up. Now, part of that's because of the way I was doing it, not the most intelligent way to make up solutions. But still, even without measuring, this takes time. That being said, let me clean up my space here really fast, and let's move on to actually doing some reactions with these. So I got to get rid of this stuff really fast. So, all right, I think that's a lot better. So let's take a look at this for a second. This is a specialized piece of lab equipment called a well plate. Well, semi-specialized. I mean, you'll find them in most labs. And it's designed to make reactions happen in a small space where I can kind of work like a spreadsheet, right? It's also nice because I don't need a lot of chemicals to use this and check it. So I think you can see what's going to happen, but we made 9 chemicals, and we're basically going to make some rows and columns where things can cross. So let's set up a first row here. So my first of these are all going to be filled with sodium hydroxide. Great, let's go ahead and build out the rest of this really fast. All right, so now this row will be sodium hydroxide, this one sodium phosphate, this one potassium iodide, this one silver nitrate. So now, like a times table, I need to go ahead and build some unknowns this way. So just to be clear, some of these things would react with each other, like silver phosphate would be a solid, silver iodide would be a solid, silver hydroxide would be a solid. But up here, these things aren't ever going to make solids by themselves, so we're not going to really react these things together. I mean, the silver is the only one that really would interest us. So we need to add the other chemicals we made in because they're more interesting. So let's build some rows up really fast, or some columns up, I mean. All right, so now you can see we've got a setup here, right? Where I take this chemical and mix it with each of these chemicals, etc., etc. Now, that on itself is kind of interesting, but as I said, and Mr. Doyle said, and Mr. Sullivan has said, what really gets us excited is not just the fact that we can make things react. I mean, that is cool, don't get me wrong, but it's that we can make it react in a way where we can predict what's going to happen. That's more exciting, right? Getting to know what's going to happen beforehand. So what we need to do is figure out if these things are going to react and then do them somewhat slowly. So, I don't know, my thought is let's start in this top corner here and work our way down, right? So in the top over here, we're going to have the reaction between sodium hydroxide and copper sulfate. Let's take a look at this. So I have NaOH. Great. Now this is what kind of reaction? All right, so I'm going to put the solubility rules on the picture here in a second. But first we need to make a prediction about what this is going to make. So I'm not going to make you predict this one. I'll predict it with you or for you. All right, so which of these two things is going to be a solid? I'm going to put the solubility rules up on the board here with the two products, and I'm asking you, which one of these two things will make a solid? So we know that we're going to get a solid made of copper hydroxide. Rule number 8, right? Hydroxides are insoluble. Anything with sodium is always soluble, so the sulfate doesn't matter to us. So we're going to get this thing as a solid formed as the result of mixing two liquids. Let's get those two liquids really fast. All right, so you can see here are the two liquids. The copper sulfate, again, is in that characteristic blue color. Over here, the sodium hydroxide. You can see there's no solids in here whatsoever, right? These are perfectly transparent solutions. Now, this is going to make a solid even though I'm starting with two aqueous solutions. We have a name for that process again. What is it? All right, so I'm going to take some sodium hydroxide, and while I'm here, I'm actually going to fill up all of the row of sodium hydroxide. So now, to that sodium hydroxide, we've predicted we're going to get copper 2 hydroxide. So let's do it. It kind of looks like something happened, but I'm not exactly sure. Here, let's prove to you that is a precipitate. Let me take some excess copper sulfate here, right? We've seen the copper sulfate. Let me go ahead and fill up all the row of the copper sulfate. All right, so as I take the light here and I shine it through all of that sodium hydroxide or all of that copper sulfate, it looks the same. But when I put it through here, you see how the light changes quite a bit? Right? Compare how that to that. So this is making it much harder for the light to get through. I know that's still not that convincing. Let me show you how I would deal with this in a lab. First, let's actually take a look at copper hydroxide together. So I've got all the extra copper and I've got all the extra sodium hydroxide here. So let's mix those up really fast. And you can see that I get this weird gel looking thing. You see that? It doesn't really look like a solid. It just kind of looks like, I don't know, shower gel or something. Let's cut this for a second and let me show you how a chemist would actually deal with this. Because I'm not sure that's a solid or a weird mixture. I predicted it's a solid. I've seen it enough time that's a solid, but let's prove it's a solid. All right, so as I hold it up to the light here, it does look kind of solid. And as I bring it closer to the camera here, you can see it's kind of like this opalescent, viscous gel, but I'm not sure that convinces me that's a solid yet, right? Like I want to prove your prediction right. You might have seen your doctors use something that's this. It's a centrifuge. And if a chemist is unsure whether or not something is a solid, we might spin it really, really fast and figure out if it's a solid that way. So let me get my phone up so I can use two hands really fast. 1 second. All right, so again, here's the before. I'm going to load that into one side. And then opposite of it, I'm going to add some water as a ballast to make sure this thing isn't unbalanced. If you think like a washing machine, if you just put something in, it's going to shake itself apart. I'm going to close the lid, then I'm going to turn it on, and I'm going to spin it here. I'm going to probably time-lapse this for a second, but I'm actually going to run it for 2 or 3 minutes here in the lab.
5 minutes later.
Now, this is very useful because it forces all the heavy things to the bottom and the lighter stuff to the top. So over here is my ballast, not useful. And then here is my, and you can see, oh wait, look at that. It's completely separated into a clear liquid layer on top, right? And at the bottom is my precipitate. It's definitely a solid. There's no question about it, right? So our prediction was right. Even if it took us a little bit of extra work to prove, here we are. Let's go back to the table. So that was only 1 out of 20 reactions that we need to do. So let's quickly come down and do the rest of this column. So every reaction is going to involve our copper sulfate. So here we're going to have copper sulfate mixing with sodium phosphate, potassium iodide, and then silver nitrate. So if I don't form a precipitate, if nothing forms as a solid, then no reaction happens. So how would I show that? All right. So these are the 3 reactions that are going to happen. Let's take a look at this one really quickly. So here's my complete ionic equation, right? The sodium and the sulfate are going to bond, and the copper and the phosphate are going to bond, right? Now, the sodium sulfate I can immediately ignore. Why? This one's a little harder though, right? I can't just say, oh, it's not going to make a precipitate. I need to actually combine these two things together. So let's do that really fast. I have Cu2+, and this should be red, but I was stupid. So I'm going to make this big compound here, copper 2 phosphate. Now, is that a solid? Use the solubility rules. I'll flash them up on the screen. All right, so let's check our hypothesis. Hey, look at that. Really beautiful color change. I mean, okay, look, it's kind of brown and ugly. But we got a color change, right? A color change is a definitive sign of a reaction. Let's take another look at the reaction. Let's come down here to this next row, potassium iodide and copper sulfate. All right, so here's my complete ionic equation, at least the reactant side, the side that's interesting. Is this K plus going to react with the copper or the sulfate? Right? They're going to trade partners. The I was with K, so now the I is going to go with the other plus, kind of like this. Okay, so again, I can ignore the sulfate because it's attaching to a 1A metal. The sulfate's never going to make a precipitate, so I need to focus on the copper. So if I look at copper and iodine, I get these two things. And I have copper 2 iodide. Now, we can look at the solubility rules, and we can say, oh, is that going to be a solid? So let's do that one more time here for a second. Let me flash them up on the screen. Well, let's take a quick look. Let's see if we're right. And sure enough, if you look, it's not as obvious as the other one, but there's very clearly a milky solid forming here. Okay, that's a precipitate. And it's what we expect, and it's not great. We could, again, go centrifuge it down. Actually, hold that thought for a second.
Future Mr. Nendick here. So you might have noticed a pause. What was going on there is I recognized that I put the wrong chemical in the wrong little bin. Right? The brown one is actually going to be the copper iodide, and this light blue one is the copper phosphate. I just put them in the wrong spot. It's not going to change anything in reality. Just know if you actually wanted to look at copper iodide in real life, it would be that brown color. So just to be clear, what I'm centrifuging right now is actually copper phosphate.
There we go. So I grabbed this and I just centrifuged it, and you can see very clearly that it was in fact a solid, right? This is very clearly liquid on one side, and down here is the rest of the chemical. Now, this time, I can ignore the copper, because the copper is going to bond with a nitrate. And what do we know about all nitrates? So now the question is, does this make a solid? So I need to combine them, okay? Ag2SO4. I'll use my rules for precipitates, check that, and then let's see what happens. And I don't see much happening. So this one isn't as obvious. Let's grab a test tube really quickly and spin it, but I want to point out that this is why we do labs. But check it out. As I do this, I do get a bit of a precipitate. It's not obvious. I don't need to centrifuge that one down. It's kind of there, right? Okay. Not the easiest thing. And so one of these things to notice is just because we say something happens in lab doesn't necessarily mean it's going to be the easiest thing to prove. Let's go across the top and do all of these sodium hydroxide reactions before my pen bleeds through or whatever. Okay, so first off, we're going to ignore any of the sodium, right? The sodium, it doesn't matter what these are. It's always going to be soluble. We're only looking at this hydroxide, right? So really, the question is OH minus going to make a precipitate with iron, potassium, ammonium, or lead? Now, I can throw two of these out immediately because without any exceptions, they are always soluble. So pick the two things that I know won't make precipitates. All right, let's prove that to ourselves. Here's some ammonium chloride. No obvious color change. I'm going to take a clean pipette here, just pull it back up. Nothing there, right? Okay. And we also don't think the potassium nitrate is going to do anything, right? So here's some potassium nitrate. And sure enough, that one's also really clear. Okay. By the way I've asked the question, it's pretty clear that these two things are going to make a precipitate. But let's predict exactly which two we're going to get. Let's start with this iron hydroxide, right? The NO3 minus and the sodium, they don't play any role, right? We said that whatever forms these things, right? I'm going to make sodium nitrate in this case. That chemical doesn't really matter. It's aqueous. Nothing really happened there. These things don't participate in the reaction. Much like someone who goes to a game and watches the athletes perform, these are called what kind of ions? But I do have these. And if I didn't know where to get these ion charges for, where would I probably look for that? So I think we're going to make iron 2
hydroxide.
Let's take some iron. It's characteristically orange. Let's add it to our hydroxide. Ooh, pretty. I mean, kind of not pretty, but like, on the other hand, very clearly, let me get a clean pipette here. I'm going to pull it up for you just to see in this pipette. Very clearly, that is full of just solid sand-looking stuff. I don't know if that's really obvious to you, but here in person I can see like little grains of it. Again, this is one of those things where if I spun it down, well, I guess it's better to show than to tell. You might be able to hear that in the background when I spin it down really quickly. Let's look at this last reaction. Sodium hydroxide reacts with lead nitrate, specifically lead 2 nitrate, PbNO3 2. So we know that sodium nitrate is going to be a spectator. We know it's going to be a spectator because all sodium's always soluble, all nitrate's always soluble. So we know we're dealing with the PbOH. And of course, in this case, we're going to get a compound, PbOH2. Again, if I don't understand where this PbOH2 is coming from, it's because when these things go into water, they actually split apart into their fundamental constituent ions, right? The things that make them up. And these two things find each other, and they make this solid. All right, so I've got my lead nitrate here and my hydroxide here. So if I go over to the guide and I look, here's some lead. I'm going to add it here, and I should get a precipitate. Let's see what happens. Hey, look at that. It looks like milk, right? Again, I don't need to spin these all down, but very clearly this is a milky white precipitate. That is no longer transparent. You can't see my finger through it, right? We got our precipitate. Now, you've seen what we've done. We're working our way down, but we're starting to get better. We're able to predict it. Now, while we're here, let's go grab that out of the centrifuge. Right? Here's our iron hydroxide. You can see, again, it's separated out. Anytime I get a precipitate, I could spin it down and prove it's a solid like this. Right? If I want to separate. Now, I did add a little water to this just to make it more obvious of that separation, but it should be clear what's going on here. All right, so now let's do this phosphate row. And I don't want to hit this home too much, but I'm only going to look at the phosphate ion. Why? So I'm going to add the phosphate ion to these four things. But look, nitrate, nitrate, chloride, nitrate. I can ignore all of the anions because they're always soluble. Do you see the way this experiment is set up is I can check, hey, are these things here going to react with the phosphate ion because it's the only thing that could possibly make a solid. Put another way I can say is only these cation ions, these positive ions, have a chance of making a solid with these things. The way they're set up, right? All right, so let's write these complete ionic equations really quickly. Cool. What's this one going to form? Of course, this one's going to make potassium phosphate. This one, ammonium phosphate, kind of a weird chemical. And down here, I'm going to make lead 2 phosphate. Just so we're there, go ahead and tell me what the chemical formula for that would be. All right, now using your solubility rules, tell me which of these things is going to be a solid. Go ahead and click all of them that apply here. All right, so let's do them in order really quickly. Let's try our iron phosphate first. Okay, some iron and here our phosphate. So here's our phosphate ion. And hey, look at that, a nice cloudy, milky white precipitate. Let's go ahead and add the phosphate to all of these. Okay, let's check it with our potassium nitrate next. As predicted, no reaction. How about some ammonium chloride? As predicted, no reaction, right? No color change. And now let's try our phosphate with our lead. Now we're expecting this to make a precipitate, so let's see. And hey, look at that. It turns white and solid looking. Very, very different than these clear ones, right? Not bad. We made some really good predictions. All right, let's do some of the ions next. Let's clean this up for a second. Now again, I'm ignoring the K, which means everything will need to bond with the I minus. While we're here, what's the name of the I minus ion? So again, these are irrelevant ions. We're ignoring the K and these anions because I know they could. Now, if I looked and I saw this was like a sulfate, I couldn't ignore it anymore. But because it's a nitrate, because it's always soluble, because it's a chloride, because it's almost always soluble, I'm going to ignore them. Again, that wouldn't necessarily be the case, but I'm dealing with a K here, so like it works here. All right, I need to combine these things. At this point, I think it's old hat, but let's just give you a free point. Combine Fe2 plus and I minus. And while we're here, let me just do the other ones for you really fast. All right, so I want you to look at rule 3, I think it is on your iron sheet, and determine which one of these or which ones of these are soluble. So which one of these will dissolve in water? So our prediction here is the only solid should be lead 2 iodide, that this will be soluble, that this will be soluble, that this will be soluble. That's not so hard to check, right? Here, I've got some Ki. Let's fill up all of our rows. And I want to combine them. Let's start with the iron. That's nice and easy. So we're predicting that this does not make a reaction. It looks like a reaction, Mr. Nendick. But here's the trick here. This is our first tricky one, right? And I want to get enough here to prove it to you, because watch what happens when I try to centrifuge this down. Check this out. And here's our first weird result. Now, we said this would not make a precipitate. And check it out. It didn't make a precipitate. See how you can still see my hand through there? See how it didn't separate out into a clear layer and a solid? Even though there was a little color change and all that going on, even though it kind of looks like grasshopper spit, nothing there. No chemical reaction in terms of making a precipitate. So our prediction was right, even if it looks a little confusing. All right, let's do the other ones. They're a little easier. We want to check Ki and KNO3. That one should be a really easy reaction. Again, we don't expect a reaction, and we don't get one. Let's check our ammonium chloride. No reaction as expected. And then our lead 2 nitrate, which is now becoming a reaction we're familiar with. Turns bright yellow, right? That gorgeous reaction. Now, we've been doing this reaction a lot, and I think it's good to see it spun down really fast. I've got the Ag plus ion this time. It's a little different than what we've done so far, because earlier we were focused on the hydroxide, the phosphate, the iodide, because these things always dissolve. But now this always dissolves, so we need to look at the thing that doesn't dissolve, the silver, at least sometimes. And where I compare silver with, well, silver, these front things don't matter, right? Because the pluses are going to mix up with the nitrates. So we're looking if silver makes compounds with these things. Now, if you look, I have a nitrate, and a nitrate. It doesn't matter what it's attached to, right? Because here I've got lead 2 nitrate, but the lead doesn't contribute anything. It's only the nitrate. Here I've got potassium nitrate. But the potassium doesn't change the reaction. It's just the nitrate I need. Here I've got iron nitrate. The iron doesn't change anything. It just makes that. But check it out. This plus that, this plus that, this plus that. What do you recognize it's going to make compared to this? If I take a little bit of iron nitrate here, and I add it to the silver, nothing happens, right? It just gets diluted. Or I could take a little bit of the lead or the potassium. Nothing happens because, of course, all three of these make the chemical I'm trying to start with. Well, that's not going to ever react. I'm making the thing I'm trying to do. You know, this is a no reaction. This is a no reaction. This is a no reaction, right? But here, if I have Ag plus Cl minus, well, then I'm going to get AgCl. And AgCl, I'll look at rule 3. What's it going to do? Make a precipitate or not? So let's try it. Will you look at that? That is a milky white precipitate. I know it's kind of hard to see there, but against my hand you can see it's very clearly a solid, right? Don't really need to centrifuge that down. Silver chloride, classic white thing. By the way, I had that potassium iodide. And there we finally go, right? Definitive proof that that is a solid. Coolio. Now, I want to give an idea of what my workspace looks like at the end of carrying out 20 reactions and trying to film them. So let me switch to a different camera really fast. And that's a pretty big yikes, right? Actually doing chemistry requires a lot of setup and cleaning. And yeah, these weld plates make it a lot easier, but I want you to imagine carrying that all out in like a test tube rack like that. It would be awful, right? And how do you keep track of which things you've used and which things are clean or not? That's the challenge of it. Now, as I said, I made one goof. I'm 99% sure this is the iodide and this is the phosphate here. In reality, it doesn't matter. Both are going to make it precipitate with copper, so, oops. But that's where we are. And sure, when we're done with the section of what we centrifuged, if I take this thing and I bring it up, oh, look at that. I can look through them, and the ones I can see through didn't make precipitates, right? And the one I can see through that's colorful, the one with my finger in it right now, that's not a precipitate. Ooh, little contamination there. And so there we are. We actually have made a basic analytical chemistry. Now, what I could do is from this test now, I could give some unknowns and ask you to identify what's happening next, right? But this video is long enough, and it's basically the weekend now, and you had your sophomore retreat. We're good. So I'm going to just snap my fingers here and... Now I guess I have to clean it up for real. That's unfortunate. All right. Well, I hope you have a great day. See you later. Bye.